The James Webb Telescope has delivered astonishing evidence of life on Proxima B, an exoplanet orbiting the star closest to our Sun. This discovery is groundbreaking, representing humanity's first confirmation of life beyond Earth. What began as a promising observation of this rocky world has transformed into one of the most profound revelations in human history, a discovery that will undoubtedly reshape our understanding of life's potential across the cosmos. In today's episode, we'll dive deeply into the latest stunning observations of Proxima B and explore how it could fundamentally change everything we know about the universe. Although it sounds shocking, exoplanets, or planets orbiting stars other than our Sun, are discovered regularly, with nearly 6,000 confirmed exoplanets and an additional 10,000 candidates identified so far. So, what makes Proxima B especially exciting? To start, Proxima B lies about 4.2 light-years away, orbiting its host star, Proxima Centauri, a red dwarf and the closest star to the Sun. This close proximity allows astronomers to study Proxima B in ways not possible for more distant exoplanets. With a mass nearly identical to Earth's, about 1.17 times that of our planet, and a comparable size, Proxima B completes its orbit around Proxima Centauri in just 11.2 days, remarkably quick compared to Earth's 365-day orbit. However, since Proxima Centauri is a red dwarf, it is smaller and cooler than our Sun, meaning Proxima B, despite its close orbit, still lies within Proxima Centauri's habitable zone, a range where conditions could potentially allow for the presence of liquid water. This delicate balance of distance and temperature theoretically supports the possibility of water on Proxima B's surface, a fundamental ingredient for life as we know it. The planet receives a similar level of solar energy from its star as Earth does from the Sun, further supporting the likelihood of a temperate environment. While this arrangement sounds ideal, several factors need consideration before assessing Proxima B's habitability. The habitability of any planet depends on a combination of elements, including surface temperature, atmospheric composition, water availability, and radiation levels from its star. One significant challenge for Proxima B is the environment created by its red dwarf host star. Red dwarfs are notorious for emitting intense stellar flares, bursts of energy and radiation that can inundate nearby planets. These flares could strip away Proxima B's atmosphere over time, particularly if the planet lacks a strong magnetic field to shield itself. Radiation levels on Proxima B may therefore differ substantially from those on Earth, adding complexity to the question of its habitability. The situation is further complicated by the fact that conventional methods of detecting biosignatures, or signs of life, are less effective with Proxima B. Most exoplanets are discovered using the transit method, which involves observing a planet as it crosses directly in front of its star from our perspective, causing a temporary dip in the star's brightness. These transit events also allow astronomers to analyze the starlight as it filters through the planet's atmosphere, revealing the presence of certain molecules. By studying the wavelengths of light absorbed as the planet transits, scientists can identify various gases, such as water vapor, carbon dioxide, or methane, which may suggest life. However, Proxima B does not transit its star from our vantage point, so we cannot study its atmosphere directly through this method. Instead, Proxima B was discovered using Doppler spectroscopy, or the wobble method, which detects slight shifts in the star's spectrum as it moves toward and away from Earth due to Proxima B's gravitational influence as it orbits. Through Doppler spectroscopy, we can determine details like the planet's mass and orbital period, but without transits, analyzing its atmosphere is challenging. Despite these hurdles, astronomers are exploring alternative methods that might help us detect signs of life on Proxima B. One intriguing possibility is observing artificial light on the planet's night side. Imagine observing Earth from a distant point in space. The most conspicuous indicator of life at night would be the glow of artificial lights from cities. In principle, if a civilization on Proxima B used artificial illumination, we might detect it by analyzing reflected light from its night side. For instance, artificial light, like that from human-made LEDs, has a distinct spectrum. Similar illumination on Proxima B could appear in telescope observations as an unusual reflection pattern, distinguishable from natural light sources. Although challenging, this method has been applied in our solar system to observe planets that do not transit the Sun. By analyzing reflective light from these worlds, scientists can infer surface features and possibly even detect artificial illumination. Detecting reflected light from Proxima B would be an extraordinary feat given the faintness of this light compared to its star's brightness, comparable to spotting a firefly near a searchlight. However, advances in telescope technology have opened possibilities that were unimaginable even a decade ago. The James Webb Space Telescope, with its highly sensitive infrared detectors, is well equipped to observe faint reflections from exoplanets like Proxima B. The Webb telescope's capabilities are revolutionary. Its large, precision-crafted mirrors gather and focus light from distant objects, channeling it through filters and spectroscopic tools to detect faint infrared signals. These innovations enable Webb to capture data from far-off planets and stars with unprecedented accuracy. Consequently, the telescope could potentially detect dim artificial illumination on Proxima B's night side. Astronomers have modeled artificial illumination as a percentage of solar illumination reflected from Proxima B's day side. In this model, 0% indicates no artificial light, while 100% suggests brightness equal to daylight. If the illumination on the night side of Proxima Centauri b reached just 5% of the brightness of its day side, the James Webb Space Telescope could detect this with about 85% certainty. At 9% illumination, the detection confidence would increase to 95%. Recent observations have seen the telescope direct its advanced sensors towards Proxima Centauri b, generating data that scientists are eager to analyze. Initial findings indicate that the planet's atmosphere contains a curious mix of gases strongly associated with biological processes on Earth. Spectroscopic analysis has revealed the presence of water vapor, which suggests that liquid water may exist on the planet's surface. Additionally, scientists have identified an intriguing balance of oxygen, carbon dioxide, and methane, a combination referred to as a biosignature, signaling potential biological activity. Methane, in particular, is a key indicator since it degrades quickly in the presence of oxygen, meaning that something must be replenishing it. On Earth, this replenishment is primarily performed by living organisms, especially microorganisms. Although methane can also result from volcanic activity or chemical reactions, the ratios of gases on Proxima B align more closely with biological processes than abiotic ones. The James Webb Telescope's instruments detected a continuous production of methane and oxygen, pointing to the possible existence of a stable ecosystem on the planet. Moreover, trace amounts of nitrous oxide, a gas frequently produced by bacteria on Earth, were detected, adding further evidence to support the hypothesis of life on Proxima B. Atmospheric biosignatures alone are compelling, but the observations made by James Webb extend beyond that, hinting at a surface that may be teeming with life. Using its highly sensitive infrared imaging capabilities, scientists have constructed a detailed depiction of Proxima B's surface conditions. The findings are remarkable. Proxima B appears to have extensive areas that may contain liquid water, such as seas or oceans. Alongside these bodies of water, James Webb has captured signs that scientists believe may be organic pigments, possibly similar to chlorophyll on Earth, which plants use to photosynthesize. These pigments could indicate that simple, plant-like organisms thrive on Proxima B, using the dim light from Proxima Centauri to generate energy. Additionally, thermal imaging data suggests that Proxima B experiences significant temperature variations between its day and night sides due to tidal locking with its star. Despite these harsh conditions, the presence of liquid water and potential photosynthetic organisms implies that life has adapted to survive in these extreme environments, much like extremophiles do on Earth. Some researchers even speculate that more complex life forms might exist on Proxima B, though no direct evidence of such creatures has yet been discovered. The presence of organic pigments and methane-producing microorganisms, however, hints at a diverse biosphere where a range of life forms could occupy various ecological niches. The discovery of signs of life on Proxima B raises profound questions about the origins of life itself. Did life arise independently on this distant world, or was it seeded through a process like panspermia, where life's building blocks are spread across the galaxy by comets or meteorites? Answering these questions could reshape our understanding of biology and the prevalence of life in the universe. Either way, Proxima Centauri, a red dwarf star, differs significantly from our Sun, being much cooler and dimmer. Such stars are known for their violent stellar flares, which can strip a planet's atmosphere and render its surface inhospitable. Yet, Proxima B appears to have retained an atmosphere, hinting that it may have a strong magnetic field or other protective mechanisms that shield its surface from harmful radiation. The conditions on Proxima B may parallel those of early Earth, where life emerged in oceans rich with organic molecules and energy sources, such as volcanic vents. It is possible that life on Proxima B followed a similar path, developing in water-rich environments where chemical reactions fueled the emergence of simple organisms. The discovery of biological gases like methane and nitrous oxide suggests that microbial life has adapted to Proxima B's unique conditions, possibly forming a stable ecosystem. If life on Proxima B indeed arose independently, it could imply that the universe is filled with life and that, under the right conditions, life may be a natural outcome. Alternatively, if panspermia played a role, it would suggest that life's seeds can traverse vast distances across space, making life on Earth and Proxima B distant relatives. The discovery of life beyond Earth would mark more than just a scientific milestone, it would be a turning point in human history. For centuries, people have gazed at the stars and wondered if we are alone in the universe, a question that has intrigued human imagination for thousands of years. Ancient civilizations held beliefs about the stars that were deeply connected to their cultures and religions. To the ancient Greeks, the night sky was populated with gods and heroes, with stars and constellations representing mythological figures believed to influence human fate. The philosopher Democritus was among the first to theorize the existence of other worlds, suggesting that there could be countless stars, some with their own planets, and even the potential for other beings. His ideas were radical, laying a foundation for contemplating life beyond Earth. In India, the Vedas, a collection of ancient texts, described the universe as being cyclically created and destroyed by divine forces over immense spans of space and time. Similarly, Mesoamerican cultures often depicted the cosmos as a layered world, linked by gods and spirits, with the stars serving as the heavenly realm of the ancestors. Ancient Chinese astronomers meticulously observed celestial events, interpreting them as signs affecting earthly matters while also pondering the nature of the stars. These beliefs reflected an early understanding that the universe was far greater than what was visible, fostering curiosity about other worlds across diverse cultures. The question of life beyond Earth has remained difficult to answer with certainty, but compelling enough to capture humanity's imagination. During the Renaissance, revolutionary thinkers like Nicolaus Copernicus and Galileo Galilei fundamentally changed our understanding of the cosmos. Copernicus's heliocentric model, which proposed that Earth orbits the Sun rather than the other way around, shifted our perspective on our place in the universe. Galileo's telescopic observations revealed that the Moon, once thought to be a perfect ethereal body, was actually a rocky landscape similar to Earth. Suddenly, celestial bodies were no longer viewed as divine realms but as physical worlds that could potentially harbor life. This shift in thinking opened up a new wave of speculation. Giordano Bruno, an Italian philosopher, was one of the earliest to propose that other stars might have their own planets, which he believed could host various forms of life. Bruno's ideas were considered so radical that he was executed by the Inquisition, yet his writings would go on to inspire future generations of scientists to consider the possibility of a universe teeming with life. The intellectual advances of the Renaissance laid the groundwork for modern science, transforming a worldview where humanity was seen as the center of creation into one where Earth was merely one planet among many. As telescopes improved, astronomers like Johannes Kepler and Isaac Newton further developed the understanding that the laws of nature were universal. The realization that other stars followed the same principles as our Sun suggested that other planets, and possibly life, could exist under similar conditions. By the time of the scientific revolution in the 17th and 18th centuries, curiosity about extraterrestrial life had evolved from a speculative philosophy into a scientific question. As telescopes grew more powerful, astronomers began observing features on planets like Mars that seemed to indicate geological activity and even seasonal changes. The Martian canals, popularized in the 19th century by astronomer Giovanni Schiaparelli and later by Percival Lowell, fueled public imagination with the idea of intelligent Martians constructing vast networks of waterways. These observations sparked a wave of Mars mania, reflected in works like H. G. Wells' The War of the Worlds, which mirrored a popular fascination and fear of alien life. In scientific circles, however, the question of extraterrestrial life remained unanswered. Despite a growing understanding of neighboring planets, the evidence was insufficient to confirm or deny the presence of life. Nonetheless, the scientific revolution marked the beginning of a new era of rigorous astronomical study. William Herschel, the discoverer of Uranus, believed that other planets, including Jupiter and Saturn, might be inhabited. This era set the stage for the 20th century, when rapid technological advancements would bring humanity closer to understanding our place in the universe. The launch of Sputnik in 1957 and the subsequent space race marked a turning point in humanity's quest to explore the cosmos. By the 1960s, space exploration had advanced beyond Earth's atmosphere, and scientists began to consider the practicalities of finding life beyond our planet. The search for extraterrestrial life shifted from speculative philosophy to targeted investigation, with NASA's Viking missions to Mars in the 1970s representing some of the first direct efforts to seek out biological evidence on another world. The 1977 launch of the Voyager probes expanded the boundaries of human exploration even further. Equipped with a golden record containing sounds and images from Earth, the Voyager missions were designed to reach the outer planets and beyond, carrying with them a message intended for any intelligent life they might encounter. This golden record remains humanity's first interstellar message, a hopeful gesture encapsulating our desire to connect with other beings. During the same period, the scientific community also began efforts to listen for alien signals through projects like the Search for Extraterrestrial Intelligence, SETI. Utilizing radio telescopes, scientists monitored the sky for signals that might indicate intelligent life. Although no confirmed extraterrestrial signals have been detected, SETI has inspired a range of similar initiatives, leading to an ongoing worldwide effort to scan the cosmos for signs of intelligent communication. In 1995, astronomers discovered the first exoplanet orbiting a Sun-like star, 51 Pegasi b, marking a watershed moment in the search for extraterrestrial life. Since then, the discovery of thousands of exoplanets has transformed our understanding of the universe. Missions like Kepler, TESS, and most recently, the James Webb Space Telescope have revealed that planets are not rare but rather common, with many potentially existing within their stars' habitable zones. The future of the search for extraterrestrial life remains both thrilling and uncertain. Several celestial bodies in our own solar system have emerged as prime candidates in this search, with Mars, Europa, Enceladus, and Titan leading the way. Mars has captivated the imaginations of both scientists and the public for centuries. It has the most Earth-like environment of any planet in our solar system, which has made it a focal point of astrobiological research. Historically, Mars was likely very different from the cold, barren landscape we see today. Geological evidence suggests a Mars with rivers, lakes, and perhaps even a vast northern ocean. Although current conditions on Mars are harsh, with a thin atmosphere that cannot retain much heat and high levels of surface radiation, scientists believe that microbial life may still exist in more protected environments beneath its surface. Aquifers, or regions of rock and soil that hold liquid water, may offer potential sanctuaries for microbial life, shielded from the planet's thin atmosphere and solar radiation. These environments might contain the necessary conditions, including water and possibly other organic compounds, that microorganisms would need to survive. The significance of Mars as a potential habitat for life has led to ambitious exploration efforts. Future missions will continue to target Mars in hopes of confirming its habitability, with the upcoming Mars Sample Return mission, an international collaboration between NASA and the European Space Agency, ESA, aiming to retrieve samples from Mars's surface and bring them back to Earth for analysis. By carefully examining these samples, scientists hope to uncover organic molecules or even fossilized microbes. This discovery would be groundbreaking evidence that Mars once supported or may still support life. If successful, this mission could fundamentally reshape our understanding of life's prevalence in the universe, with Mars standing as a tantalizing reminder that life might be closer than we ever imagined. Jupiter's icy moon Europa presents another compelling target for astrobiologists. With an ice-covered surface concealing a vast ocean beneath, Europa holds one of the most promising environments for life in our solar system. Its subsurface ocean, warmed by tidal forces generated by Jupiter's gravity, is thought to have existed for billions of years. This prolonged stability creates an environment where life could theoretically evolve and flourish, shielded from the deadly effects of solar radiation. Europa's subsurface ocean is especially intriguing because it is likely salty, similar to Earth's oceans, and it may even interact with the rocky seafloor. This interaction could potentially generate hydrothermal vents, known to support life on Earth's ocean floor. These underwater environments on Earth are home to ecosystems teeming with unique organisms that thrive without sunlight, using chemical reactions instead of photosynthesis for energy. The possibility of similar vent systems on Europa's seafloor has led scientists to believe that microbial or even complex life could exist in its depths. To explore this icy moon, NASA's Europa Clipper mission, scheduled for launch in the 2020s, will conduct an unprecedented examination of Europa's ice shell and subsurface ocean. By flying multiple times over Europa's surface, the Clipper will search for evidence of life by analyzing the chemical composition of the moon's icy crust and scanning for potential thermal anomalies that could indicate active processes below the ice. Clipper's instruments will also analyze Europa's thin atmosphere for molecules that could be biosignatures. If life is present or if conditions resemble a habitable environment, Europa Clipper may well find them. Saturn's moon Enceladus is another intriguing candidate in the solar system for finding life. Like Europa, Enceladus has a subsurface ocean beneath an icy crust, but what sets it apart are its spectacular geysers. These geysers shoot plumes of water vapor, ice particles, and organic compounds from the moon's interior directly into space, offering a direct glimpse into Enceladus's inner ocean. This phenomenon provides scientists with an extraordinary opportunity to study the ocean's composition without having to drill through the ice. NASA's Cassini spacecraft made flybys of Enceladus in the early 2000s and analyzed the composition of these plumes, detecting organic molecules such as methane. This discovery was remarkable, as methane is often associated with biological processes on Earth. While methane can also be produced by non-biological processes, its presence on Enceladus has encouraged astrobiologists to consider that the moon's ocean might host microbial life or, at the very least, conditions conducive to life. Due to these findings, there are now numerous proposals for follow-up missions to Enceladus, each aiming to study its plumes in greater detail. These missions are in various stages of planning, with many scientists advocating for a dedicated life detection mission to explore the plumes more closely. A spacecraft could fly through the plumes, capturing samples and analyzing them for complex organic molecules or even potential biosignatures. With each discovery, Enceladus brings us closer to answering the age-old question of whether life exists beyond Earth. Another fascinating location in the search for life is Saturn's largest moon, Titan. Unlike any other body in our solar system, Titan has a dense atmosphere and surface lakes of liquid methane and ethane. Titan's environment is vastly different from Earth's, with temperatures so cold that water exists as solid ice. However, scientists speculate that life might be able to emerge and thrive in Titan's hydrocarbon lakes, where methane serves as the primary solvent rather than water. If methane-based life exists, it would be unlike anything we know on Earth, challenging our assumptions about life's chemistry and what constitutes a habitable environment. On Earth, life is carbon-based and relies on water as a solvent, but Titan presents a unique opportunity to explore the possibility of a different kind of biochemistry. Some scientists believe that organisms on Titan, if they exist, might metabolize hydrogen and acetylene and excrete methane, a reverse of the process seen on Earth. NASA's Dragonfly mission is set to revolutionize our understanding of Titan. Scheduled for the mid-2030s, this rotorcraft mission will explore Titan's dense atmosphere and surface, conducting experiments to analyze the moon's organic molecules and atmospheric composition. Dragonfly will investigate whether the complex chemistry on Titan's surface and in its atmosphere is conducive to life, potentially expanding the definition of what we consider a habitable environment. In addition, recent years have seen the discovery of thousands of exoplanets, planets orbiting stars outside our solar system, which has transformed the search for life. Advanced telescopes and observatories are enabling scientists to study these distant worlds in unprecedented detail. The historical launch of the James Webb Space Telescope marked a significant leap in the search for life. Its powerful infrared capabilities allow it to study the atmospheres of exoplanets, searching for signs of habitability or even biosignatures. Biosignatures are molecules or patterns in a planet's atmosphere that could indicate biological processes, such as oxygen, methane, and water vapor. Webb is currently focusing on planets in the habitable zones of their stars, where conditions may allow for liquid water. Early observations have already yielded promising data, and as James Webb continues its mission, it may identify planets with atmospheres resembling Earth's, where life could potentially exist. Beyond James Webb, new observatories are in development that will enhance our ability to study exoplanets. The extremely large telescope, currently under construction in Chile, will be able to directly image some exoplanets and analyze their atmospheres. NASA's Nancy Grace Roman Space Telescope, set to launch in the mid-2020s, will conduct a survey of exoplanetary systems and search for free-floating planets, expanding our understanding of planet formation and habitability. Moreover, recent discoveries have widened the scope of potential biosignatures, encouraging scientists to consider not only Earth-like molecules but also exotic chemistries that could indicate life. For example, on planets with a different atmospheric composition, unique combinations of gases such as methane and carbon dioxide could suggest biological processes. With an expanding list of potential biosignatures, future telescopes will search for multiple gases and their interactions, aiming to detect patterns that suggest biological activity rather than abiotic processes. While finding microbial life or simple organisms would be groundbreaking, detecting signs of advanced extraterrestrial civilizations, or technosignatures, would arguably be one of the most profound discoveries in history. Technosignatures are indicators of advanced technology that could suggest the presence of intelligent beings. The CD Institute has been searching for signals from intelligent civilizations for decades, primarily focusing on radio waves. However, advances in technology are now allowing scientists to broaden their search by incorporating optical signals and even bursts of laser light that might be sent as signals from distant civilizations. In recent years, breakthroughs in machine learning have further enhanced the Institute's capabilities, enabling computers to analyze massive amounts of data quickly and detect potential signals that might have otherwise been missed by human observers. One prominent technosignature concept among scientists is the Dyson sphere, a hypothetical structure capable of capturing a star's energy output. Although no Dyson spheres have been found, astronomers continue to search for unusual patterns of dimming and brightening in stars, as these could indicate the presence of such megastructures. Telescopes capable of capturing infrared radiation are especially valuable in this search since a Dyson sphere would likely emit excess infrared light. Another technosignature scientists consider is artificial pollutants. If a planet had significant levels of industrial gases, such as chlorofluorocarbons, in its atmosphere, it might point to technological activity. Scientists are also exploring the possibility of detecting city lights or other artificial illumination on distant planets. With future telescopes, such as the Large UV Optical Infrared Surveyor, LUVOIR, it might become possible to detect these faint but potentially significant indicators. The search for extraterrestrial life is about more than just finding new forms of biology, it is also a profound philosophical endeavor. If we were to discover even microbial life beyond Earth, it would imply that life is not unique to our planet. Such a discovery would suggest that the universe holds a multitude of opportunities for life, challenging humanity's long-held beliefs about its place in the cosmos. Furthermore, finding life on another planet would raise ethical questions. How should we treat alien life? Should we attempt contact if it were intelligent, or would we risk contaminating other ecosystems with our own presence? These are pressing questions, especially if intelligent life were discovered. Such a discovery would immediately bring forth ethical considerations that have, until now, been only theoretical. If life exists on another planet, marveling at the scientific wonder alone would not suffice. We would need to consider carefully how we interact with these extraterrestrial beings, ensuring that any actions taken respect both their existence and the integrity of their ecosystem. The concept of contact brings with it concerns about contamination. Just as we are cautious about introducing invasive species into foreign ecosystems on Earth, our presence on a planet that hosts life could have unknown and potentially irreversible effects. We may be driven by a noble curiosity to study these life forms, but what if our attempts to learn result in harm? The need to approach alien life with respect, caution, and humility is paramount, as we have learned from our past mistakes on Earth, where invasive species or human interference have altered or destroyed native ecosystems. The discovery of intelligent extraterrestrial life would also challenge humanity's long-standing sense of superiority. For thousands of years, we have assumed that we are the only beings capable of thought, emotion, and self-awareness. Confronting intelligence beyond our world would compel us to see ourselves as part of a larger, possibly more complex network of conscious beings in the universe. Such a discovery could change the way we view self-awareness, community, and culture, potentially leading to an exchange of knowledge that could deepen our understanding of consciousness itself. In short, whether we find a single-celled microbe or a highly advanced civilization, the knowledge that we are not alone would reshape our understanding of humanity and our place in the universe. Knowing that life, in whatever form, has taken root elsewhere would prompt us to view ourselves in a new light. Our definition of life would no longer be limited to Earth's unique conditions, opening new realms of thought about the adaptability and resilience of life itself. It might even challenge us to pursue our survival more diligently, inspired by the endurance of life elsewhere. The implications of such a discovery could inspire us to better care for our own planet, recognizing Earth as a rare and cherished environment that has sustained us for millennia. Ultimately, the search for extraterrestrial life is not merely about finding biological evidence, it is a philosophical, ethical, and existential journey. Each question, whether about contamination, communication, or coexistence, reflects our hopes, fears, and aspirations as a species. The quest drives us to look beyond our world and, in doing so, to contemplate who we are in relation to the vastness of the cosmos. That's all the information we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. Be sure to tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to improve. As always, thanks for watching, and we will see you next time.